Ever heard of a cosmic blob or smudge? Meet Abell 2744, a colossal cluster of galaxies nestled billions of light-years away, serving as a gateway to the universe's secrets. But what makes Abell 2744 truly captivating isn't just its sheer size, it's the universal lens it provides, bending and magnifying light from distant realms, allowing us to peer farther into space than ever before. Thanks to the Hubble and James Webb Space Telescopes, we've uncovered an enigmatic gem within this cosmic tapestry, UHZ-1, the ultra-high redshift galaxy, a relic from the dawn of time itself. Join us as we delve deep into the infrared hues of UHZ-1, a celestial time capsule revealing the universe's infancy. Through the lens of science, witness the breathtaking spectacle of galaxies stretching back over 13 billion years, echoing the very birth of our universe. Prepare yourself as we unravel the cosmic ballet choreographed by gravity and light. Stay tuned, and don't forget to subscribe to our channel for more mind-bending adventures. The really exciting moment came when we pointed another orbiting satellite at the smudge. This is the image by the Chandra X-ray telescope. It turns out there are a lot of X-rays coming from this little blob. Now, X-rays are much harder to bring to a sharp focus, so the 4 pixels of X-ray light aren't coming from across this spread-out region, but rather from somewhere inside this region. There's really only one known way for a galaxy to be blasting out X-rays at this level, and that's by harboring a quasar. To refresh your memory, a quasar is when the supermassive black hole that lives at the center of every galaxy starts feeding. As matter swirls towards the black hole, it's superheated until it outshines the entire surrounding galaxy. And just before it reaches the black hole, conditions get so crazy that the space outside the black hole glows bright with high-energy X-rays. Based on the amount of X-ray light and the distance, we can estimate that the black hole must be 40 million times the Sun's mass. That's 10 times the mass of the Milky Way's own supermassive black hole. UHZ-1 is the most distant quasar ever discovered, which also makes it the earliest known quasar, and so the earliest black hole that we actually have evidence for. To understand why UHZ-1 is so exciting, you have to understand one of the biggest debates in cosmology, the origin of supermassive black holes. Essentially, every galaxy in the modern universe has at its core a black hole that's 100,000 to several billion times the mass of the Sun. We also see much smaller black holes, so-called stellar black holes, that can be in the rough range of 10 to 100 solar masses. Oddly, we don't see black holes in the middle range of 100 to 100,000. Now, we know how to make stellar black holes. They're what you get when the core of a massive star collapses on itself after the star dies. So how do you make supermassive black holes grow? That's the big question. It could be that they grew from the very first stellar corpses in the early universe, gulping down gas and merging with other black holes for billions of years to reach their current enormous sizes. But over the last decade or so, as we looked to greater and greater distances, we started to find quasars shining out from the first billion years of cosmic time, quasars powered by supermassive black holes that should not have had enough time to get that big. There are 2 potential solutions to this conundrum. Either the black holes started small and grew way faster than we thought they could, or they started much bigger than the black holes that form in stellar deaths in the modern universe. These are the small seed and heavy seed models, respectively. UHZ-1 is going to help us choose between them. As the small seed model suggests, can a stellar corpse grow into a quasar engine in less than 1 billion years? Well, it's tricky. There's a limit to how fast a black hole can feed, even with an endless supply of gas. As gas spiraling into a black hole heats up, it blasts out radiation, which pushes on the infalling gas and counters the black hole's gravity. Bigger black holes can eat more and radiate more, but there's always an approximate upper limit that increases with that mass. It's called the Eddington limit. You can calculate how big a black hole would grow, feeding at this maximum rate for 1 billion years, and the answer is not big enough to explain those early quasars. There are various tricks we can include to make the small seed model work. There are scenarios in which black holes can feed faster than the Eddington limit, although they still need to feed non-stop to reach supermassive status so quickly, which itself is a problem. Or you can form a lot of black holes close to each other and have them merge very quickly. Or you can start out with really big stars, leaving behind black holes that are maybe 100 or even 1,000 times larger than are produced today. In the modern universe, all the heavy elements released in past supernovae cause gas clouds to fragment as they collapse, leading to smaller stars. But the pristine hydrogen and helium that filled the universe at the beginning held together as it collapsed, probably leading to gigantic stars and commensurately massive but still not supermassive black holes. With a combination of these tricks, fast and consistent feeding, and biggish stellar black hole seeds, it's possible to make supermassive black holes in under 1 billion years. This still doesn't explain why we don't see any black holes in the 100 to 100,000 solar mass range. If supermassive black holes grew from stellar black holes by passing through this range, then you'd expect some stragglers to still be in that range, but that doesn't seem to be the case. So let's try the heavy seed model. What if the seeds of supermassive black holes weren't even born from the hyperdense cores of dead stars? In fact, it's actually a misconception that you need extremely dense matter to make a black hole. For any given mass, there's a particular size that mass needs to be crushed into in order for it to form a black hole. This is the Schwarzschild radius. For the Sun, it's around 3 kilometers, and a solar mass crammed within that radius would have the same density as a typical 3,000-meter tall mountain, crammed into a cubic centimeter. On the other hand, a typical chunky, supermassive black hole of 1 billion solar masses has a Schwarzschild radius the size of Neptune's orbit. 1 billion suns crammed into that region would have the density of cotton candy. That's right, fill a solar system with cotton candy and you'd get an instant giant black hole. The early universe was filled with a lot of gas that would later form stars and galaxies. So, what do you think? The heavy seed model might just be the missing piece in understanding the birth of supermassive black holes. We've journeyed through captivating theory, but our exploration doesn't end here. Dive deeper into the wonders of space science with our channel, and we will keep sharing latest updates and learnings about this discovery. Subscribe to Space Episodes for upcoming educational videos related to space science, and press the bell icon. Thank you for watching this video until the end.